Good morning, Year 12 single mathematicians. Just going to start chapter 11 from the mechanics book on variable acceleration. The first subchapter is to do with functions of time. Up until this point we've done acceleration and it's always been constant. We did it for Suvat equations where everything was moving in a straight line, and we also did it with vectors, but still stuff was always constant acceleration and it wasn't a function of time. But for this subchapter it is going to be a function of time, and I just want to remind you of some of the key things. So up to this point, when we were doing Suvat, everything was moving in a straight line. So we still got an object moving in a straight line. So still objects moving in straight lines. Just like the Suvat equations. But the thing is now, where for Suvat, if I drew a velocity time graph, VT graph, time velocity. If you remember, for a velocity time graph, acceleration was the same as the gradient. So for Suvat stuff, we would have all straight lines, something like that. Okay, so all of this would be examples of constant acceleration. Okay, so this is constant acceleration. Gradient is equal to the acceleration. And in this particular subchapter, we're going to have VT graphs which are actually curved. So it could be curved something like this, or it could be curved the other way. And then if you worked out the gradient of this at different points, the gradient is always changing, which means the acceleration is always changing. So variable acceleration, because gradient is changing. And that's pretty much it. Okay, so we're going to cover this stuff. We've done all of these in a previous chapter. Now we're going to cover all of these. So the first example is the following. We have a body moves in a straight line such that its displacement, s meters, from a point O at time t seconds is given by this formula. So displacement is equal to 2t cubed subtract 3t. And that's for t is greater than or equal to 0. And we would like to find out what s would be when t is equal to 2. So pretty straightforward part A. We've got the formula and we replace the letter t with the number 2. So s would be equal to 2 cubed subtract 3 2's. And if you type that into your calculator, 2 cubed subtract 3 2's gives you 10. So the displacement is 10 meters. And then part B, the time taken for the particle to return to the origin, to O. So remember, displacement is relative to some point, some starting point, which is O in this question. So you want to return back to O, so you'd like the displacement to be 0. So in other words, S is equal to 0. And you generate an equation. 2t cubed subtract 3t is equal to 0. And then from pure maths, you should know how to solve this type of equation. It's a cubic, but it has a common factor, and you factorize. The t brackets 2t squared subtract 3 is equal to 0. And then you can say either t is equal to 0 or 2t squared minus 3 is equal to 0. Now it's obviously not that time, is it? Because t is equal to 0 is already at the starting point, so the time taken for it to return, well, we can ignore that one for this question. And if you make t the subject in this, you get t is equal to plus or minus the square root of 3/2. And in the context of this question, we ignore the negative. You can't have a negative time, they even tell us there. Can't have a negative time. So t would be equal to the positive version of this, and it's good to write this to 3SF in mechanics, so 1.22 seconds. And that would be it. Okay, one more example. Okay, so we have a body moves in a straight line such that its velocity, this time v meters per second at time t seconds, is given by this. And you can see this velocity is a quadratic, which is a curve. So this is one of those examples where we've got a curved velocity, so there's going to be a variable acceleration. So to find the initial velocity, that's, in other words, make t is equal to 0. And if you take v and you replace every t value with 0, you get 24 meters per second. Pretty straightforward start. Part B, find the values of t when the body is instantaneously at rest. So just for one instant, the body will be at rest. In other words, the velocity is equal to 0. Okay, just for a moment. And then sub that in, we get 0 equals 2t squared subtract 16t plus 24. We've got a quadratic. Before I try to solve, I'm going to divide by 2. And to be fair, in mechanics, you can just go straight to your calculator and solve it using your calculator, but it's always good practice to do factorizing. And I'm going to actually skip a few steps with this and go straight to the answer for the factorizing, which looks like it would be minus 6 minus 2, to give you two values of t, 2 seconds and 6 seconds. And that would be when the body is in, for an instant, at rest. Okay, a couple more parts to go with this. Find the value of t when v is equal to 64 meters per second. So 64 is equal to 2t squared subtract 16t plus 24. Another quadratic. You always try to make quadratics equal to 0. If you see a common factor for an equation, you can divide by it. So divide by 2. And then probably factorizes. And it goes to minus 10 plus 2 to give you two possible values. Either t is equal to 10 or t is equal to minus 2. And obviously, because t is a measurement for time in the context of this question, we ignore that because t can't be negative. And part D, the hardest part by a long way, is to find the greatest speed of the body in the interval t is between 0 and 5 seconds. So the greatest speed. Now, for speed, it doesn't matter whether the velocity is positive or negative, it's just like the biggest number. A velocity of, say, minus 5 meters per second has a higher speed than the velocity of 4 meters per second. So I want the biggest number positive or negative. And the way you're encouraged to do these is by a sketch. That's exactly what I'm going to do. So sketch the quadratic. Done quadratic sketches before, so we are going to do that. We start off with the shape. This is a positive quadratic, the one right at the start. If you remember, that one all the way back there is a positive quadratic. So look like this. Then you work out the y-intercept, or in this case the v-intercept, which we worked out in part A. Actually it was 24. So when t is equal to 0, v is equal to 24. Then you work out the x-intercept, so in this case the t-intercept. If you put y is equal to 0 in, or in this case v is equal to 0, we actually worked that out in part B. That gave us 2 and 6. And then that's enough information to draw the sketch. So let's draw the sketch. It goes through 2. It goes through 6. It would have the minimum halfway, 4. And it would go through 24. And it looks something like this. And that would be the quadratic. Now, t-axis, v-axis. We only want the interval 0 to 5. So 0 is there, 5 is there. And we just want that section of the curve there. Don't care about this, don't care about this. In that section there, I want the greatest speed. Well, it kind of looks like this, doesn't it? It looks like the 24. 24 is definitely the highest positive velocity, but I want to know what this minimum is. And I've kind of given it away there because this curve is perfectly symmetrical. It would happen when t is equal to 4. So I've just got to check when t is equal to 4. So just check t is equal to 4 and see what value that would give me. V would be equal to 2, 4 squared, subtract 16 fours plus 24, which is equal to 2, 4 squared, subtract 16 fours plus 24, gives you minus 8. And that speed is not quick enough. So the greatest speed in that body, in that interval would be 24. Greatest speed equals 24 meters per second. Would be that. And pretty much that would be it. Now I want you to practice some questions from the textbook. So if you find exercise 11A, which is on page 184, I would like you to do, let me get this right, the odds, and the odds only, just the odds on page 184. Okay, let me know how you get on. Make sure you upload your work to the class notebook and post any questions on the Teams chat. Thanks very much. Enjoy.